research, we are trying to bring a new approach for vegetable tanning by using an enzyme-assisted process. So let's start from the start. I apologize to my audience, but I had to start saying that tanning is the conversion of hides and skins into leather, because this work is about tanning. And one of the characteristics that tanning gives to hides and skins is increasing its hydrothermal stability. And by increasing the hydrothermal stability is a way of measuring this increase in hydrothermal stability is by measuring the shrinkage temperature. So the higher the shrinkage temperature, the higher is the hydrothermal stability. And this is a characteristic that is wanted for the leather. So in some level, we can say that by increasing the hydrothermal stability or by increasing the shrinkage temperature, we are also increasing the cross-linking, the stabilization, and the tanning reactions. Okay, so in this work, the way that we are measuring the tanning effect of our process is by measuring the shrinkage temperature. So vegetable tannings, they are widely used for leather tanning and retanning as extracts from natural products. And a problem of this process, or a disadvantage, is that these natural extracts, they are highly reactive with collagen, which means the process must be carried out very carefully and in diluted solutions, and it takes a longer time to complete. And that's one of the reasons why this process was replaced by other faster and most cost-effective tanning agents, such as metal tanning. Just to remind you, vegetable tannings, they are biomacromolecules or polymers that they have phenolic hydroxyls that participate in hydrogen bonding with collagen and then creating the tanning reactions. They are subdivided into hydrolyzable and condensed. The most common ones used for leather, for hydrolyzable, are tala and chestnut, and condensed are quebracho and mimosa. So hydrolyzable tannings, they are linked by ester bonds, and as the name says, they are hydrolyzable or broken. They can be broken more easily in their ester bonds here. We have condensed tannings. That is mostly the focus of my PhD. Condensed tannings, they are polymers of flavontriol, which is this structure here. And they are linked by more stable carbon-carbon bonds. So it's a little bit more difficult to break these polymers. And the increase in shrinkage temperature that is given by tanning with condensed tannings is between 20 and 25 degrees in relation to native collagen. In terms of size is really important when we talk about vegetable tannings. The molecular weight of these molecules should be considered as a tanning and participate in cross-linking with collagen must be between 500 and 3,000 daltons. But why is that? Because if these molecules are smaller than 500, they have deficient tanning action. So they cannot cross-link two molecules of collagen together, because those reactions are what make the tanning happen, the cross-linking between different collagen molecules. So if the tanning molecule is too small, they will not react in an efficient manner. And if they are too big, bigger than 3,000 daltons, they have penetration difficulties. So the ideal range of molecular weight is between 500 and 3,000. Here we have some monomers of condensed tannins. As you can see here, for example, catechin is a monomer of procyanidin type tannins. Catechin is the monomer, procyanidin is the polymer. And catechin has a molecular weight of 290. So it means that it has a deficient tanning action compared to the polymer. Just to illustrate, we have here propicetinidine tannins. They are present mainly in quebracho tannins, and porobenectinidine are present in mimosa tannins. So from these monomers, a way that nature transformed them into tannins is by enzymatic catalysis. And that's the idea for this work. We want to mimic the nature and use enzymes to transform smaller molecules into bigger molecules. So these reactions of polymerization, they can be performed by polyphenol oxidases. So they are enzymes that will act in the phenolic moieties of these compounds. And this enzyme will generate a free radical from the phenolic species. And then these free radicals, they can combine and react after non-enzymatically, and then can form dimers and oligomers and polymers. The mechanism of this reaction, so it's a polycondensation reaction. And the first step is the formation of free radicals by the enzyme. So this part is controlled by the enzyme kinetics, and the enzyme is very specific and is going to act on the monomers. After the formation of free radicals, these free radicals can then combine. Two monomers can combine to form a dimer. Then the enzyme will continue to act on the monomers. Then another step is the transfer of a free radical from a monomer to a dimer. And then we have the growth of the chain by alternating these steps, transferring the free radicals and recombination, and then we can form the polymer. So the aim of this part of my research is to apply smaller phenolics. So these smaller phenolics, they have the advantage of penetrating faster. One, because they are smaller molecules, so they can reach the spaces between collagen molecules more effectively. And second, since they are not as reactive as a tannin, they can penetrate faster. And then, after penetration, we try to polymerize them using an enzyme and creating these tannin-type reactions for the stabilization of collagen. So for this, we did two steps. So first, for us to know how the enzyme was acting on these monomers, we did some kinetic studies on the disoxidation or polymerization of the monomeric phenols. And then after this step, we've chosen one phenol to be applied on high powder and perform the enzymatic enzyme-assisted process. So first is the kinetic studies. So for these kinetic studies, we chose catechin, catechol, and paragallo to be our sources of monomeric phenols. The measurement of the appearance of the product was made via spectrophotometric determination. Initial velocities of the reaction was the linear part of the curve absorbance space-time, the slope of the linear part. And this initial velocity was then transformed into enzyme activity. This is just a little bit of theory on how to measure the kinetics of enzymes. Those graphs, they are called the Michaelis-Menten graphs. So we have here velocity according to substrate concentration. And from this graph, we can obtain two parameters: the maximum velocity represents for us that more product is formed per minute, and Km is the enzyme substrate affinity. So by definition, Km is the substrate concentration in which the velocity is half the maximum velocity. And what's really important here, the lower the Km, the higher is the affinity of the substrate with the enzyme. So here we have the Michaelis-Menten graph for our 3 monomers. Just by looking at the graph, we can see that catechin has here a higher maximum velocity. And then, if we invert this graph, which means we divide 1 by the enzyme activity here, and here divide 1 by substrate concentration, we get the Lineweaver-Burk plot. From this graph, it transforms the Michaelis-Menten graph into lines that can be adjusted. We adjust here and obtain an equation. And with this equation, it allows us to calculate the max and Km. So here in this table, we have the calculated values for our 3 phenolics. So here we can see that Parabello has the lower Km, which means it has the higher affinity with our enzyme. But we can see that catechin has a higher maximum velocity, which is forming more product. So then by looking at these parameters, we decided to use catechin as our source of monomeric phenols. And another advantage of catechin is that it is a monomer for condensed tannins. So since condensed tannins are already used for leather manufacturing, so this is closer to what we already use. So then that's why catechin was chosen and then applied for the enzyme-assisted process in the stabilization of collagen or tannin. So then in this part of the research, we compared our enzyme-assisted process with the control. This control, we had only catechin applied, because catechin in some level can impart some stabilization to collagen. So in order to compare if our enzyme-assisted process was better than applying just catechin, we did a comparison with this control. The degree of tannin was then measured by the shrinkage temperature, as I said at the beginning. And the measurements were made using differential scanning calorimetry, and the shrinkage temperature was the onset in the thermograph. So here we have our results. The first bars here are the controls, so only catechin applied for different catechin concentrations. And the second bar is the enzyme-assisted process. So as you can see here, we had a significant difference for all catechin concentrations between our control and the enzyme-assisted process. And also we had here a significant increase from 40 to 80 millimolar of catechin, but not significant the difference between 80 and 160 millimolar of concentration of catechin. Okay? So for those of you who like statistics, I have a table here with the statistical analysis of this graph, of what we can observe in the graph. This is confirming from the statistical analysis that control versus enzymatic is highly significant, the difference. And here you can see that between 40 and 80, 40 and 160, the difference is significant, but not between 80 and 160 millimolar. But then we were thinking, what if, since here we used 40 milligrams per liter of our enzyme, we thought maybe 160 millimolar of catechin will require more enzyme. What if we use more enzyme, we can obtain a higher increase in shrinkage temperature using more catechin. And this is the result. We increased from 40 to 80 and 120, and no significant difference was found. So for these conditions that we had in the process, 80 millimolar of catechin and 40 milligrams per liter of enzyme was enough for reaching the maximum shrinkage temperature that we could reach with this process. So our preliminary studies, now just summarizing everything, our preliminary studies show that the catechin had higher velocities with our enzyme, and then therefore it was chosen as our monomeric phenol for the tanning experiments. And for our tanning experiments, we analyzed that the enzyme-assisted process presented a significant difference when compared to our control with only catechin being applied. And in our process, the increase in shrinkage temperature using the enzyme was found to be between 19.5 to 20.6 approximately. And if you remember what I said at the beginning, condensed tannins give an increase in shrinkage temperature between 20 and 25 degrees. So here with our enzyme-assisted process, we are reaching shrinkage temperatures that are similar to the ones achieved by using condensed tannins, the normal condensed tannins that we already use for making leather. So in conclusion, this work indicates that there is a potential for applying biotechnology in creating tannin reactions, and the monomeric phenols can make the process happen faster and enabling vegetable tannin to compete maybe with other tannin agents. And this is a new approach for vegetable tannins, for a vegetable tannin process. Here's some references. I'd like to thank you, Tanya and Matt, for helping me with the experimental work, ICLT, and CNPq from Brazil for giving me the scholarship. Thank you very much for listening.